A set is a collection of objects. That's not a new idea to us. After all, we talk about having a set of tires on our car. Each of the individual pieces of that set are called an element. So with a set of tires, each individual tire is an element of the set. When we count the number of elements in a set, we call that the cardinality of the set. So the cardinality of a set of tires on our car is 4. When we look at sets, we're often going to look at sets of numbers. So let's talk about some particular sets. The natural numbers are also called the counting numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and we could keep going on and on and on because the natural numbers never end. Within that set of natural numbers, we can also talk about even numbers. That would be 2, 4, 6, 8, 10, and so on. Or the odd numbers, which would be 1, 3, 5, 7, 9, and so forth. The prime numbers are numbers that have exactly 2 different divisors. So the prime numbers would be 2, 3, 5, 7, 11, and they also continue forever. Multiples are numbers that we find by skip counting. So for example, the multiples of 3 are 3, 6, 9, 12, 15, and so on. We have different ways to write sets of numbers. One way is called the descriptive method. That's nothing more than writing words to describe the set. So in this case, we could say that this set is the set of natural numbers. Roster notation is a list of the elements in the set. For the natural numbers, since they're an infinite set, we'll have to have a way to show that within the notation. In roster notation, the natural numbers look like this. Now there's a couple of things to notice. First of all, the individual elements of the set are separated by commas. Secondly, because this is an infinite set, we need to show that the set goes on forever and ever. That's what the 3 dots mean at the end. The 3 dots are called ellipses, and they mean that the pattern that we're seeing continues on. Lastly, we need to show that this list of numbers is a set, and we do that by surrounding the list of numbers with curly braces. Set builder notation might look familiar to you if you remember seeing it from algebra. To write the natural numbers using set builder notation, we would write this. Now the way we would read that is the set of all x such that x is an element of the natural numbers. Now let's look at another set. This set contains the numbers 2, 4, 6, and 8. You'll also notice that this set has a name. It's set A. When we name sets, we use capital letters. While the natural numbers were an infinite set, this is a finite set because it does not go on forever. If we write this set using descriptive notation, we would write A equals the set of even natural numbers less than 10. And if we write it using set builder notation, we could write A equals the set of all x such that x is an element of the natural numbers, x is even, and x is less than 10. Because set A is finite, we can also count the number of elements in the set. So in this case, we have 1, 2, 3, 4 elements in the set. Now we've already said that that's the cardinality of the set. But we have some special notation we can use to indicate that we're looking at cardinality. And that's this notation. So when you see the n and then in parentheses the name of the set, that means the number of elements in set A. And in this case, the number of elements in set A is 4. Now take a look at this set, set M. You'll notice that there's nothing inside the curly braces. That's because this is a special set called the empty set. It's a set that contains nothing. And if it contains nothing, then the number of elements in the empty set is equal to 0. We can write the empty set using empty braces, but we can also write the empty set using a special symbol that looks a lot like a 0 with a line through it. That symbol means the empty set, so be a little careful with that. A 0 with a line through it means the empty set. A 0 means the number 0. Now we've already looked at these two sets, set A and set M. Both of those sets are considered well-defined. A well-defined set is a set in which we know exactly what is in the set and what isn't in the set. This set, set L, is the set of all large numbers. It's not well-defined. That's because we don't really know what's in the set. What's a large number? Is a large number 100? Is a large number 1,000,000? Is a large number 10? Since we're not really sure what a large number is, we've got a description of the set that is not well defined. Finally, we've got ways that we can compare sets. When we compare sets and we notice that they have exactly the same elements, we call them equal sets. Set A contains 2, 4, 6, and 8. Set B contains 6, 4, 2, and 8. They are exactly the same elements. They happen to be in different orders, but that doesn't matter. What's important is that the elements are identical. So set A is equal to set B. Equivalent sets are sets that have the same number of elements. In other words, they have the same cardinality. So if set A is 2, 4, 6, and 8, and set C contains W, X, Y, and Z, the two sets are equivalent. They are not equal, they don't have the same elements, but they do have the same number of elements. To write that two sets are equivalent, we use this special symbol. So this says A is equivalent to C.